layers and all that. So that's more advanced.
Okay.
Just a heads up.
Is NLTK libraries involved?
Well, I don't really mind like using libraries there. It's more about conceptual things.
Okay.
So it's more about advancing knowledge rather than the tools you are actually using. But yeah, so feel free to enroll and you will see in the first couple of lectures I will tell you exactly what this is about.
Cool.
Is that the artificial intelligence class?
No, that's even basic than this one.
Oh.
But the spatial topic I'm offering next semester is natural language processing. That is advanced. So this is kind of like in between. If you need a more like basic one, that's the artificial intelligence. If you need a more advanced one, that's the NLP, advanced topic.
Are you teaching the artificial intelligence also?
Next semester, yes.
Oh, the online one?
No, the in person.
Oh.
It should be online as well. I mean,
I have a hold because I have a hybrid model.
all right. So in the last class, we were talking about SVM. How many of you have heard about SVM? Like, this is a thing that you know. You heard about it. That's good. And how many of you remember this formula that I'm showing here? How many of you don't know what this is, this equation is? Okay, so looks like you kind of know what this equation looks like. But just as a brief cap, this equation actually came from here. Not this, right? We had a quadratic optimization problem with some linear constraints. And we said like we could use a quadratic programming tool, which may not be very efficient, but we can still solve this problem, right, on the top. It's a quadratic programming problem. There are tools to solve it already. But we said we are interested in something more efficient or more like computational, more empirical. And as computer scientists, we love gradient descent. And for gradient descent, we cannot have like that kind of constraints while we optimize, right? We just need one convex kind of function to do gradient optimization, right? Gradient descent. So we could translate that optimization problem into a single objective function. That's what we showed in the last class, right? So this is exactly essentially the same thing without any constraint. This is just the optimization function itself. And that's where we stopped. And we said there is a problem. Well, there is always a problem, but here the problem was we want to do gradient descent, and we have a max here, which is not differentiable. And that's kind of a problem. We will see how we can solve that. But the good thing is now instead of all those like a quadratic function and some constraint, we have a single function. If we can compute the gradient of this, we can do gradient descent. That's the point. The challenge is max is not differentiable. So computing the gradient of max is a problem. All right. And then we said, right now, our single objective function that we have has two components, right? The one on the right is basically the empirical loss. That is basically coming from the hinge loss. We talked about hinge loss, right? That one is coming from the margin. And then you have a dot product exactly between, like the perceptron, right? Yi w times x. That's the perceptron kind of thing. But the hinge loss is a max between 0 and 1 minus of that. That is our empirical loss. We want a w that minimizes that loss. But that's not all. We also have a w squared term that we also want to minimize to maximize the margin. And that exactly looks like a regularization term. How many of you have gone back home and reviewed what regularization was? None of you. Excellent. So, again, I cannot review everything that I taught in regularization, but the whole point is this is L2 regularization where you are trying to optimize, minimize the square of W. That basically means you are trying to find a W that has minimal minimal value, magnitude in the Euclidean space. That basically means if there is one solution like this, and there is another solution like this, you will prefer this one because this has a smaller magnitude, the W. Okay. Remember, W is no longer a unit vector, so you can go arbitrary with W, but the smaller the W is, the larger the margin is. So you probably even want a W that is even smaller than a unit vector. Okay. So now this is basically an objective function where we are combining Hinge laws with some regularization, some L2 regularization. And the parameter C is basically a hyperparameter that is defining your weight between your regularization term and the empirical loss. We covered all of this in the last class. So C is the hyperparameter. So that's good. So now the point is, I think I want to switch back to presenter view. That helps me predict what is coming next. Yeah. So now the question is, we want to optimize this thing, so we must, as a computer scientist, we love gradient descent. We want to do that. And in order to do gradient descent, the function has to be
Differentiable.
and yes, and convex. Because without a convex function, you cannot do descent, right? I mean, it has to have a global minima, and then you have to go to the direction that actually minimizes the function value. It has to be convex. What was the definition of a convex function? How does it look? So does it look like this? Does it look like this? Does it look like this? Which one? Number 3, right? So convex functions look like that. And the good thing here is wherever you start, you can start descending by computing the gradient, right? So essentially convex functions look like the one in the middle. The left is a linear function. The right is a max function. Is that convex? The max function, is that convex? Is that differentiable? Now, is that continuous? Is that continuous? Well, that is continuous. There is no discontinuity, but it's just not smooth. It's not differentiable at that point. So it's kind of convex, but not really differentiable. It's kind of, right? So the thing that we have to deal with this kind of max function is to handle that handle that non-smoothness, the point where it's not differentiable. That's the only challenge. Other than that, it's pretty much like if I think about this function, and this is just an extreme case of this kind of functions, this is where the problem is, right? So that's what. And there are functions that are concave like this. You just flip the convex functions, it becomes a concave function, right? Those are neither. I mean, they are a combination of convex and concave, right? So before we start, we need to find a solution for the max. So let's first simplify some notations. So you see, that's the top function that we actually want to minimize. And there is a there is a B that's kind of the offset term of the linear linear separation plane. So just to get rid of that B, we can simplify the notation like this. So W naught is essentially now becomes the W, and the revised W is basically W naught and B concatenated. So it's basically the point is the basic hyperplane at the origin is defined as W0, W naught, and the offset term B is separated out. And if we consider this augmented representation, that becomes W. So it's basically W naught is the weight vector that goes through the origin, and if I concatenate B, then it is defined as W. It's just a notation thing. There is nothing like fancy or tricky going on here. It's just a notation. So now the good thing about this notation is now we have a slightly simpler notation where the first part is just the W naught, we don't care about the B, and here this W has the B which is multiplied with the augmented representation of X. It's just simple notation thing, nothing else is going on. So given this function, we want to do gradient descent. How do we do it? We compute gradient. Let's say we start with a solution here, right? You compute the gradient at that point. So there is a tangent, and then you compute the gradient. You take a step in the opposite direction of the gradient, right? Because gradient gives you the steepest increase direction. You want to follow the opposite direction. So that's why whatever the direction of gradient is, you want to go the opposite direction. So based on this, because gradient is saying like this way it is maximized, so this must be the way where it is minimized. So W should move this direction with some step, learning rate like R. So you suppose that you went to W naught to W1, and in W1 you again compute a gradient, and you see you should further move left, right? And you keep doing this, you move to W2 and so on until you reach kind of like the minima, right? So that's what gradient descent do. And in terms of an algorithm, we have seen this many different times. That's the basic gradient descent algorithm, right? So you start with some random gradient or like zero gradient, and you update rules like this. So you update over t iterations, and at each iteration your new weights become you kind of subtract. You go to from the current weights, you subtract the gradient of the loss function, and then R is just a learning rate. You try to experiment with that. So at each iteration, your W is essentially whatever you had previously minus. The minus is because of the gradient descent. You are going the opposite direction of the gradient. And the gradient is defined as J of W. That is your loss function. And you multiply with some kind of learning rate. Simple. This is the T. Right? But still the question is, what is this? Because this is coming from, that J is coming from there, and that has a max. That's a problem. But before we come to a solution for this, one thing that we want to remind ourselves that even if we have a solution of this, that is most likely going to contain that summation over I. Right? I mean, whatever if we have assuming that we have a differentiation of max, still we have to sum over all those i's. That's kind of a problem, and that's not very efficient. So that's a real bottleneck in terms of like computing the gradient. So what we should be doing, rather than, so you remember in logistic regression, we had gradient descent, and then we had another version of the gradient descent that was kind of was shown to be more efficient. It doesn't guarantee, it's kind of like a greedy approach that doesn't give you a direction to the global minima at the single point, but it kind of gives you an efficient alternative. What was that? Right, the stochastic gradient descent, right? You remember? So in logistic regression, we had two versions. One was the batch update, where you have a batch of training data, you kind of compute a gradient based on the batch. And there was another alternative where you don't consider the batch, just one example, based on that compute the gradient, take a direction that may not be optimal at this point. But if you continue this for a sufficient amount of time, that will converge. That is shown to be converged. There are theoretical proofs. But the good thing about that is instead of n different points, you are just computing 1 point at a time. And in the long run, that saves you a lot of computation. So we are going to do the same thing here for gradient descent, which is the stochastic gradient descent version for SVM. So rather than doing that sum over I over all the examples, we don't care about all examples. We just will sample one instance at a time and compute the gradient for that point, and we will keep iterating. Rather than for every iteration, rather than going over all the points, we'll just go over 1 point, randomly selected. That's the stochastic version of the gradient descent. So pick your random sample, xy, from the training set, and repeat x, I, y, I to make a full data set and take the derivative. So what this is basically saying is, you, instead of doing that sum, you are saying like this example is actually repeated n times in my data set rather than n different samples, which doesn't necessarily mean anything. It's just a constant at the end of the day. In terms of direction, that doesn't matter, but they just assume a hallucinated data set with this single example repeated n times. But you don't have to compute that sum every time, rather than you just multiply with n here, which is again a constant. It doesn't matter. But your new function now doesn't have a sum. Now it's more efficient for one iteration. And then you update formula, and for somehow, because I was merging from two different like tutorial sources, they use a gamma t notation instead of r. It's just the same learning rate, okay? It's the same learning rate, but then you are just computing, now you are computing this loss function with respect to one example rather than n different example. That's all the difference in stochastic gradient descent. If all of this sounds confusing, here is a visual demo. So gradient descent is something like this. Let's say your global optima is here, you start from there, and if you compute the gradient over all the examples, you will exactly go to the right direction every time towards the global optima. And that's a good thing. It's just computationally intensive because you have to go over all the examples in every iteration. Rather, you could do stochastic gradient descent, where you start from a point. Maybe, based on that point, the direction you're taking there, you see, it's not going towards that minima, global minima, but it's going somewhere. And then you go to the new point, you take another direction that is not towards the global optima, but still that is kind of like a greedy approach. Right now, I should go here. But it can be theoretically proven that if you iterate over all the examples one at a time, multiple times, it will actually try to converge. It will actually converge towards that global optima that we want. So there are theoretical guarantees to this. And The good thing about this is now instead of going over all the n examples, you are going over one example. And this is, in practice, this is much more efficient than the like overall batch update thing. Okay? So you will kind of like jiggle around, but still, if you take more steps, overall your computation will be less compared to the batch learning thing. Okay? But we haven't yet solved that big problem. What was that?
The max function.
The max function problem, right? What do we do with this max function? That's something that's still, yes, it's great. We have a single function. We have a gradient descent way. We have a stochastic gradient descent that is efficient, but we still don't know what is the derivative of this. That's the problem. That's the only problem that is remaining. Any question up to this? You see the red text, the derivative of this SVM objective. That's kind of still something that's a problem. Okay, again, this problem is highlighted here, this max function. So before we talk about that, let's talk about some concepts. And so far we have been talking about gradients. Now we want to talk about subgradients. And the whole idea of subgradient is if you have like non-differentiable functions where there is a point that is not smooth, you use this idea of subgradient, which is basically like a piecewise gradient for different part of your function. So what this basically means is, let's say, consider this function. Now, this is a function where it is not differentiable because there is a point here which is not smooth, right? Now, but if we don't consider this point, if we have a piecewise function here and a piecewise function here, they are individually differentiable. Only that point, that joint point, that's where the problem is. So we can solve this gradient computation of this kind of functions with subgradients for pieces of that function. Okay? For example, if I need to compute the gradient at this point, it's fine. We'll just consider the equation of this part and we'll take a derivative. There is no issue. For this part, we can take any function, take a derivative, and we can just compute the direction. The only problem is here, where you can get two different gradients based on, if we compute gradient based on this function at this point, there will be one gradient, and based on that function, part of the function will be another gradient, right? So we just need to handle at which part we are and what gradient we need to compute. That's the subgradient idea. So essentially, we can do kind of like a if-else kind of code or case checking, where the idea is to first solve the max problem. So first figure out whether the max function gives you a 0 or a 1 minus ywx. If you get a 0, then that part is gone. All you have is the first term, w squared. Gradient of that is w. That's easy. But if your max is 1 minus that term, then you need to combine these two, right? So it's kind of like a case-by-case subgradient we need to compute because we have a non-smooth point in between, right? So the idea is if you have J T of W, there are two different cases. One is when that function yi wt xi is greater than 1. When it is greater than 1, the second term becomes negative. So the max becomes 0. So this function just becomes this. In the first case, the max is 0 because the other term becomes negative. In the second case, else, right? Well, if it is equal to 1, that is also 0, right? Else, Jt of W is essentially half Wt minus C n yi xi. Right? Just taking a derivative. Because, oh, sorry, I wrote the wrong one. I wrote the delta j. The j remains the minus C dot n yi wt xi, right? The other part, because that's the max now. Is this clear? Okay. So now, based on these two cases, we have two different gradients for two different parts. If this is greater than or equals to 1, this dot product, we have this function. But if it is less than this, we have this function. So based on this, we'll compute two different gradients for two different parts. That's the idea. Because they are convex. Like between them, there is no problem. Only the joint point is the problem where it's 1. So if we compute a gradient of this, delta Jt of W is essentially W naught. And this one, for this part, if we take a gradient that is just C dot n, the W vanishes. This is just this. So now, instead of one gradient function, we have two gradient functions, and we have to just look at what is the value of this. If this is greater than or equals to 1, we'll compute gradient this way. If this is less than 1, then we'll compute gradient this way. Okay? So that's what we have here. And we have augmented 0 here just to match with the dimension of this augmented representation. This is just a 0 value padded to this vector, nothing else. But the whole idea is you separate it out, the function, into two parts and compute gradient based on the value of the dot product for two different parts. And you can do that computationally very easily using the if-else logic. Right? So now, your subgradient, stochastic subgradient descent for SVM changes this way. So you again start with W naught equals to 0. Then you start for each epoch. For each training example in xi and yi, you are trying to update W with this gradient descent formula where your gradient descent function looks like this. So if your dot product is less than or equals to 1, you update with this formula, which comes from here, or else you do this. Where this is coming from? This is coming from the W naught is Wt delta this, right? So for this case, where this is equal to just W naught, right? So you have for when the dot product is greater than or equals to 1, you have this, which is essentially 1 minus gamma t of W naught. This is what you see here, right? But if this is less than 1, then the formula becomes this, which is equal to W naught minus C n y xi, which is equal to W naught gamma t W naught plus gamma t C n y I xi, which is equal to 1 minus gamma t W naught plus gamma t C n y I xi. This is what you see here. And again, 0 is just augmented just to make it same size. Okay? Questions? So we'll just do the stochastic subgradient. We'll do one example at a time. We'll compute the gradient at that point. But in case of gradient here, we'll compute subgradient because it's not smooth at a particular point. So we first need to see which point are we in. And based on that, we have to choose one of the two options of the gradients. That's what we are doing based on this choice. So everything remains the same, only your gradient computation now have an if-else instead of a continuous function. And in case of stochastic gradient, the order at which you receive the examples actually matters because that's how you choose your direction. So you want to randomize these things. So every time you go over an epoch, you kind of shuffle the examples so that you don't have bias in terms of the direction you're taking. It has to be random. And you can play with the learning rate gamma t, r, whatever you call it, to see its effect. So now coming back to kind of connection between SVM and the perceptron, this is the hinge loss function, remember? Right? We have been trying to optimize this max of 0, comma 1 minus this. What did we actually optimize in perceptron? We actually optimized for this, which is essentially just missing this 1. But there is one more difference. What is that? So first of all, essentially perceptron is not maximizing margin. This 1 is what helps you maximize the margin with an additional thing. What is that? What else we are doing here for SVM rather than this part? What is the other part of the optimization function? The regularization. There is no regularization here. There is no W square minimization. We are just minimizing this in perceptron with no margin, just the empirical loss, right? But here, we are maximizing with respect to a margin and with a regularization. That's kind of the connection between the loss function of perceptron and the hinge loss function in SVM. Two different things from perceptron. One is basically a margin. This 1 is kind of responsible for that. And the W that we are learning, we also have a mean squared optimization problem. Like we have a squared minimization problem of W. That's the regularization term we have in SVM. Okay? So now we have proposed a solution and an algorithm where you really don't need linearly separable data, right? Because this loss function can still work when your function, your data is not linearly separable. It will try to minimize this loss, and for the cases where you are making a mistake, it will impose some penalty, but still you will get some solution for non-separable data. But there was this question like, why not use a nonlinear function in the first place to make it nonlinear, right? But the question is, if you don't really know the true distribution of your data, because all you are seeing are training examples, maybe the true distribution is a little different. You don't know. How can you even learn the perfect nonlinear separation plane? Well, you can try to fit some nonlinearity and hope that nonlinearity with this loss function that still tolerates some mistake will do well, right? So you are now combining two different things. One is previously perceptron was not tolerating any like mix and match of data points, like it has to be linearly separable. But now we are saying we have something that can deal with non-separable data, but even with linear functions, it's not, we'll have a lot of mistakes anyway. We can minimize that by introducing some non-linearity. It will not guarantee that we will have a perfect separation, but it will kind of help us do more pure classification. There will be minimal errors because now we are allowing the function to be nonlinear itself. So combining nonlinearity with this kind of hinge loss function allows you to fit a nonlinear model with maximum margin. And how can we do a nonlinear thing with this kind of formulations? What is the trick?
Subgradients.
That's for gradient descent. What was our trick for non-linearity? Kernels, right? Because you can replace the dot product with a kernel function, and that will transform your data into phi space. In the phi space, it will still look for linear separability, but in the real space, in the current space, that will be a nonlinear function based on the kernel that you actually use. Kernel functions can take arbitrary shapes. There are different kernel functions to try. And if you combine kernel with this kind of hinge loss function, now you can fit nonlinear functions with that tries to maximize the margin. But there is one problem. What is that? Yes?
Kernel trick is n squared.
Kernel trick is n squared. That's one problem, definitely sure. That's an efficiency problem. But right now, can you plug in the kernel function here directly?
You could replace the WTX.
What was the definition of kernel function? What do you need? Dot product between what?
Two unit vectors.
Two unit vectors. Does it have to be unit? Dot product between, remember? So just tell me what was the function of k? K of what?
XZ.
Xz and
I thought Z was the second one.
z was the second one. What is the first one? Xi, yes. So that basically means two different data points. They have to be data points, not W. Here we have a label, which is a scalar, and then two vectors, which one is a weight and the other one is a point. So can you actually really use kernel trick here? Not really. You need a dot product between 2 points to actually replace for kernel functions. So that basically means all we have done so far is not useful. We need to start from scratch. We need some formulation where we have dot product between 2 points that we can replace with a kernel function. Otherwise, we cannot do nonlinearity. Good news or bad news? How many of you think this is a bad news? Is it bad or good? Well, it is bad because now you have to start from scratch. But the good thing is, we're not going to cover that in this course. But I'm going to tell you just the name of it, like how to solve it. And if you're interested, go ahead, read about it. That is called a Lagrangian dual formulation. So there is another formulation that you can derive the SVM objective function. We have talked about the top one, the primal form of the SVM. There is another form of SVM that is called Lagrangian dual. And that looks something like this. We are not going to do the derivation in this course. But the point is, now you have a formulation where you have xi and xj. And I'll tell you the intuition, because remember, W in perceptron, Wt plus 1 was Wt minus x, right? Or plus x. And we actually added or subtracted a set of xi or xj, right? So essentially, what we had was an alpha I xi as w. That is how we learn w. So if we say w dot x, that is essentially a summation of alpha I xi dot x. So you can replace w dot x with alpha I xi dot x. These are two different points. And just by following this definition of w, which is a summation over alpha I xi, you come to this alternative Lagrangian dual formulation. Just replacing w with alpha I xi. Now you have dot product between two different points, and it kind of like a slightly different constraints than that. You will just, this is just algebra we have to do, but the good thing now is you will have this dot product between two different points where you can take this out, put in a kernel function. It will do exactly the same. But now you can introduce nonlinearity by kernel functions. Okay? So the goal of this course will be just to know that there is a Lagrangian dual form where you can take dot product between two different points and you can replace a kernel function there. But the actual derivation is not within the scope of this course. Okay? And it is interesting to note that the alpha I just mentioned, this W is essentially a sum over alpha I xi, and the yi is basically this sign. So this W is defined as this, but all these alpha i's that are not 0 are defined as support vectors. And you know what? The alpha i's will not be 0 only for points that are in the boundary. For all the other points that are deeper into their region, alpha i's are essentially 0. You don't need to care about them. All you need to care about is those points that are near the boundary, because that's what decides the boundary. You don't really, when you have a set of points like this, you don't really care about this point. You are trying to maximize the margin between this set of points. And for these points, your weight, alpha, these xi's, these alpha are non-zero. These are the points where you want to put emphasis, and all the other alphas are 0. Here, these are 0. So all the points in alpha for which alpha is not 0 are called support vectors. So these are the support vectors of this decision plane that actually defines this plane. And these support vectors try to maximize this margin. Others are kind of ignored. They are ignored. They don't have a say in this decision plane because they don't matter anyway. Okay? So what you should know, the margin is kind of the central thing that comes in SVMs. That's what it tries to do. So the difference from perceptron is essentially trying to define a margin and try to maximize it. And there is a hinge loss function that we can use to maximize this, but that is not differentiable. So we use this subgradient trick to actually minimize for this hinge loss. And then after doing all of this, we kind of realize, we cannot do it kernelization with this. So there is an alternative formulation that you can do that gives you dot product between 2 points that you can replace with a kernel function to increase nonlinearity. Now you can combine nonlinearity with the hinge loss to get nonlinear complex functions, arbitrary shaped functions that tries to maximize the margin at the same time. Good? Questions? If I were in the beginning of the semester, I would have waited more, but I have to cover more content, so I'll just move forward with the next topic. So this is going to be the last topic of this course. I wanted to also talk about clustering and unsupervised learning, but I just decided not to. Okay, so we have learned about SVM, which is great. You don't need linear separation of data. You can do kernel trick to kind of do nonlinear things, and that works pretty well. What is still wrong? What is, yes?
It's only for binary classification.
Well, you can use binary classification for multi-class classification, right? Because you could do one versus all kind of classification and base your decision based on that. That is something you can still do. I mean, that's not something you cannot do with SVM. What is a more critical problem? Yes?
The computation.
The computation, why do you think that's a problem?
Like raising elements to phi space, and also we're iterating over every example and trying to get that to the greedy.
Yeah. So if you still have to, first of all, you need non-linearity, right? So that means you need kernel functions, and you have to compute that kernel function over all the example dot products and phi space kind of thing, right? So still that is computationally intensive. You need something that is linear. And that's where neural networks come in. They are very simple in terms of the basic architecture, like the basic units. It's just the network itself can complicate arbitrarily to approximate universal functions, like any function. And that there are theoretical proofs that you can kind of approximate any function using neural networks. But the beauty of it is the individual units are simple, and then you can do back propagation, which can be done in linear time. So now you have a non-linear learning function that you can do in linear time. That's kind of like what we really want. Well, ideally we might want something log n, which we don't have, but this is still something that is much better than quadratic. So linear problems that can be modularized, that can be parallelized, and all those things. So that's where neural network come in. Okay? So when we talk about like biological systems and artificial neural networks, we kind of think about, well, maybe they are kind of similar, but they are very different. Can you tell me one basic difference between like biological neurons and artificial neural network? One very fundamental difference. Not looking at the slides. Think about multiplication. Our brain, the neurons are not. So think about this. I give you a multiplication 3890 times 4576. Can you do it? No? No. It's because our brains are not trained to do multiplications. It cannot. So human brains are more like an accumulation or kind of addition and firing kind of mechanism. We accumulate signals and fire. Whereas artificial neural networks kind of try to do multiplication and make a decision and fire. That's the basic difference between artificial neural network and biological systems. There is another one. Anyone? Think about an image or even a text. You look at the image, you have an idea. You look at it for 20 seconds, you have a better idea. You look at it for 2 minutes, you have even better idea what is happening. What does that mean?
You're learning from previous things, because like
What is the fundamental thing with previous?
memory, like
Memory over
time.
Right. So biological neural network has this time evolving nature. So over time, it can accumulate learning or analyze things. In artificial neural network that we see today, well, there is a big research that tries to now emulate that time dimension of human brains. But the kind of artificial neural network we are going to talk about, don't consider that. Even if you throw that artificial neural network to an image with the techniques that we are going to learn, it's not going to change its perceptron. If its perception, like whatever it has learned, if you look at it for 100 hours, it will still give you the same prediction, unless you retrain its weights. Okay, so there is no kind of like notion of time dependency or like processing information over time in artificial neural network. It's just kind of like a one shot. is there. That's it. Okay? So it's just good to know, although we'll be using terms like neurons and everything, but that kind of neurons we are talking about are very different from what human neurons do. And that's why people today talk a lot about human-machine collaboration, because machines work in a very different way. Although we call them intelligent, they are artificially intelligent, and that intelligence is very different from human intelligence. So there will be natural things that humans are better at, and there will be things that machines are better at. So it's not about replacing humans with machines or machines with humans. It's more about taking the best of humans and taking the best of machines, forming a team, and do something. Okay? You probably have seen like images like this a lot when it comes to a neural network, right? So you have these kind of circles that are called neurons. And there are edges. It looks like a dense graph. It is actually a graph, but it's a graph of a network. And it basically, a neural network is a collection of nodes or neurons and that are connected to each other. And there are basically like 3 different things, types of neurons that neural networks have. The first is the input layer neurons. The input layer neurons. The second one is output layer neurons. And the third one is hidden layer neurons. Okay? What does that mean? It basically means an architecture of neural network is basically laid out with respect to 3 different kind of layers. One is input, one is output, and one is hidden. Now, how that looks? So maybe the first layer is an input. Let's say your input is a 3-dimensional vector. And your output is a 10-class classification problem, okay? So let's say you have 10 neurons. 1, 2, 3, 4, 5, 6. Let's say 6. 6-class classification problem, okay? And so this is input layer where you are providing your input. And this is the output you are expecting, right? So output could be one of the 6 classes where each neuron represents a class. So class 1, class 2, class 3, and so on. So whichever class is the right one, that neuron will fire, right? That will tell you, like, okay, this is the prediction for this data. And in between them, you have an hidden layer. And that's where normally all the magic happens, right? Hidden layer. That's where we do all those tricks to do this magic that neural networks do. So the input layer is kind of fixed. Based on that depends on your data. What is your task? If your data is 3-dimensional, then your input layer should be 3-dimensional unless you are creating a different set of features out of them. Whatever your feature space is, your input layer is just your feature representation. Your output layer is also determined by your task. If it's a multi-class classification problem, it's just you want some neurons to represent those classes. The tweaks you can do is in the hidden layer. And one tweak you can do is how many neurons you actually want here. And it's just not one layer. You could have multiple layers of hidden neurons, maybe one more. And then for the architecture, you need to decide what kind of connections you want to have. You can have each layer connected to its previous layer with all the neurons. Or you could say, okay, this is only connected to this. This input, this input layer this input neuron doesn't connect to any others. That is your architecture that you decide. But the simplistic one is you have connections between each possible pairs of neurons in a layer and the previous layer. And the idea is to combine all these features in some way in this hidden layers. So you're essentially creating new features. That's the idea. And that's why neural networks are also helpful for representation learning. What this means is, we have been talking about feature engineering, right? You create features from your data, but you don't really know what features are useful. Why not delegate that task to machine? Let them figure out what features are important. Let them construct those features on the fly during training. That's what these hidden layers actually do. They create complex features out of these simple features. And the next layer computes even further complex features. And even further complex features, maybe like a braid of your hair. This neuron is just doing that, right? And then in the final layer, you do computation, like you do the prediction. So that's what neural network is doing. So it's essentially creating new features inside your network that you even don't know and you haven't defined, and it's very difficult to interpret as well. But surprisingly, they work very, very well. So neural networks give you extreme power over like classification or pattern recognition, but they lack kind of explainability. How do you know why this is doing that? So that's a big criticism. And there is a big research community trying to like propose methods just to explain neural networks, why certain things are the way they are behaving. Okay? So here are some examples, right? For example, your Tesla car, right? If you think about automated driving, whatever is happening inside Tesla is mostly a neural network. Because in case of images, think about this. If you have an image, all you have is raw pixels, right? How do you combine these pixels? And how do you create features is a very difficult task. If I give you a tabular data, you have a better sense. Oh, maybe these two attributes, if I multiply and take their square, that's a useful thing. I should do that. But if I just give you an image with some pixels, what to do with those pixels? You don't really know. So then you want to use these neural networks to create those features. Maybe this Tesla has already learned stop signs, the neural network inside Tesla. It has already learned passengers, their movements, kids, animals. All those kind of features have been learned inside those networks. Maybe those are high-level features at the very end, right? Just from those pixel values. So what is the goal with our neural network? We are essentially trying to learn a function which is nonlinear, because that's how real life data looks like, that maps x to y. We are still talking about a classification problem where you have a multi-class classification problem. You have an input x, and you are trying to map that x into y, which is some labels, some classes. So x is your feature space, right? It could be continuous, it could be discrete. Y is your output space. It could be continuous or discrete as well. But right now, let's focus on the discrete case where we are talking about classification. And a network of basic units. And what this unit means is these circles, these neurons. So essentially, all that we need to care about when designing a neural network is, how does these units look like? What are their properties? What are the connections we are talking about? And at the last layer, what is our objective function? Because every time you have to minimize a loss function or optimize some objective function, right? In case of perceptron, we try to minimize the number of misclassification. In case of SVM, we try to minimize W square with the empirical loss, or we try to maximize the margin. In case of neural networks, we'll also try to do something. And one of the most popular way to do that is this mean squared loss, which is convex, right? Squared function. And what it tries to do is basically predict something, and look at the actual label, and take the difference and make a square of this. This is the mean squared loss that neural networks can optimize very efficiently. There are many other loss functions, and this is not even the best one for classification task, because this is like a mean squared loss. Do you remember where did we use mean squared loss for optimization? For which problem? Regression. You remember? In regression, we said like we cannot predict exact values, but we will try to get close to that. But you can kind of simulate that squared problem for classification as well. But here the idea is you want to learn, given this data, training data, and their labels, and TD is basically the label, train weights of W. You want to learn, because your network, once you define it, it's fixed. All you are trying to learn is this weights. What should be the weight of this network? What should be the weight of this H, right? This connection. So essentially, once you learn these weights, then your neural network is kind of deterministic. It will try to predict based on those weights. So essentially, again, we're trying to, instead of one weight W that we tried to do for SVMs and perceptrons, that's a vector. Here you can also think of it as a vector, because all the weights, if you kind of concatenate them into a single vector, we are again trying to learn that W vector that represents this network. And if we take that weights and use that to simulate this function, whatever prediction that makes, that should be as close as to the original labels. So you want to get very close to the original labels. If you don't, your squared loss goes up. So the more mistakes you make, the more loss you incur, and more changes you have to do, right? And we have already seen how to do that for one particular unit. Can you tell me where? Think about this unit. What can we replace here? Yes? A linear regression. Well, that's a problem, but what is the model that you would like to fit here from all the models we have learned here so far? Perceptron? Okay, anything else? What can we fit in here? All these units we are talking about. And we are just connecting in these units. So one suggestion is these units could be perceptron. What else? Sorry? Kernel. Is kernel itself a method? Well, you could say kernelized perceptron. Yeah. We could do kernelized perceptron. What else? Okay, what is the problem with perceptron? It's linear. Yeah. If you do kernelization, that's not linear anymore, but there are more problems. Perceptron is not differentiable, right? Can you differentiate a perceptron? No. What is the other thing that we learned that is differentiable and kind of simulates what perceptron tries to do, but with a weight factor.
Logistic regression.
Logistic regression, exactly. There you go. Right? It kind of tries to simulate perceptron, but now you have a bounded range and you have a differentiable function with an exponential. So, and that is nonlinear. That's the good thing. So now, with a logistic regression unit, you can kind of do nonlinearity, differentiable, and all that. That is kind of like a nice property, right? So, and then again, logistic regression is just a sigmoid function over perceptron. So it's exactly the perceptron with a sigmoid function that makes it differentiable, continuous, right? The good thing about sigmoid function is now you can differentiate that. And it is very important to differentiate because the loss you calculate here should be differentiable to learned weights of this layer. And you have to propagate whatever error you have accumulated back to this layer. Because like the error you see here is actually an accumulation from all these layers. So you need to kind of compute the total loss. You need to compute what this layer contributed and kind of then propagate it back to what this layer contributed and this layer contributed and so on. You need to back propagate all the errors to the input layer and then kind of try to, and while in that process you want to update these weights and then try to predict with with those like revised weights. And this process goes on and on. So it's basically, you initially have random weights for each layer, okay? For each age, all that. So you give some input, you get some random output. And based on random output, you compute some loss. That loss, you backpropagate to the previous layer and account like which node actually contributed what. And based on what this node contributed, you kind of backpropagate based on this weights. So because I'm seeing this much loss, most likely this low node has contributed this loss, this node has contributed this loss, and all that. And you keep backpropagating to the initial layers. And in that process, based on the loss, you kind of change all these weights. And then in the next iteration, you again use your input with the revised weights to make a prediction. And because we are doing gradient descent, the loss will be lower than the previous iteration. And after some point, there will be convergence if you keep iterating this process. This is called the backpropagation algorithm, which we will actually study in the next lecture. And this is kind of the backbone of neural networks, because people proposed neural networks a long time ago, and the field was stuck for a long time because nobody knew how to do optimization in a network. And then the backpropagation came and people were very excited. They did a lot of work until they realized this requires so much computation and we don't have data, we don't have compute power. So somebody from MIT wrote like neural networks are hopeless. We should quit this. And there was complete silence for over 15 years. Nobody looked at neural networks because MIT said you should not look at, right? But there are people who did not stop. Geoffrey Hinton, Jan LeCun, people who got the Turing Award, right? They kept working on that, and they did nothing else. They just worked on their problem, but the chips changed, and the amount of data, available data changed, and the same network, the same kind of architecture, same technology that was proposed in 1980s are doing magic now, okay? Just with the compute power and the amount of data. So that backpropagation algorithm we are going to learn in our next class. All right, see you on Thursday.